So again, welcome back to our latest lecture session. So we have been discussing the relevant redox reactions, the relevant applications and the relevant terminology in the last couple of sessions. So today we are going to discuss the relevant aspects with respect to kinetics and then move on to equilibrium, right. So before we go further, again let's just refresh what it is that we have been up to in the last couple of sessions. So I guess we looked at understanding what is oxidation, right. And we know that it is the process of donating electrons yes, and reduction process of gaining or accepting electrons, right. So oxidation again process of donating the electrons, and reduction process of accepting the electron. So obviously by accepting the electron, what would you expect with respect to the change in the oxidation state or oxidation number of the relevant atom here, right. So you are gaining the electron, right. So the oxidation state is going to be obviously, or oxidation number is going to be reduced, right, or it is going to decrease. So obviously if you are donating the electron, what is going to happen here? The oxidation state, right, of the relevant atom, it is going to increase here, right. So again in reduction, process of accepting the relevant electron or gaining the electron, right. So because your particular atom, let us say, is gaining the electron, so you can obviously try to understand that the oxidation number is going to be reduced or decrease. And with respect to oxidation, obviously because you are donating the electron or loss of electron, right. So you are going to observe an increase in the oxidation state of your particular atom here, right. So I guess here we have two examples. One would be obviously here, this is the process of donating the electron. So this would be relevant example for oxidation, and this particular half reaction is where we have process of accepting of the relevant electrons, right. So that would be a particular example for reduction, right. So again here we have glucose being what is it now, oxidized by oxygen, right. So obviously let us look at the try to understand the relevant system here. So here obviously oxygen is an electron acceptor, right, and that is what you see from this particular half reaction. It is an electron acceptor or an oxidizing agent, and this is something you need to keep in mind, because oxygen obviously prevalent everywhere, right, or in most natural systems, right, and obviously its role is that it is an electron acceptor, right. So either it plays a role in most of the reactions itself, or sometimes you want to inhibit its role as an electron acceptor, but we will look at those aspects later on, I guess. And here obviously we see that glucose is leading to release of what do we say, electrons. So here let us say it is playing the role of a reducing agent, right, one which can donate its electrons. So again electron acceptor and electron donor, right. So obviously in this process of donating the electron, what is going to happen to this particular carbon oxidation state in glucose? You see that it is going to be increasing here, right. So or it is going to be oxidized. So the reducing agent in the process of donating the relevant electrons is going to be oxidized. So now let us look at oxygen here, I guess, right. Oxygen is accepting the electron, it is an oxidizing agent. So it is going to oxidize the other compound, right, but it is going to be reduced itself, and that is what you see here. Oxygen is accepting the electrons, right, and being transformed into, let us say, H2O here. And obviously if you calculate the oxidation state, we are going to look at a decrease in the oxidation state here, right. So obviously if you look at that, oxidation state of oxygen here is 0, right, and here it is going to be equal to -2, right, and obviously you see that it is a decrease in the oxidation state here, right. So 2 electrons per each oxygen atom, I guess. So here this is obviously something that you need to be comfortable with, and I am sure you will get that particular, what do we say, familiarity, let us say, with respect to the terms as you go along, right. So let us look at what else we have looked at, I guess, right. So we also looked at applications, right, and I believe we looked at applications, and we looked at various cases, I guess, one with respect to wastewater treatment, with respect to ferrous removal, arsenic removal or such, right. So I am not obviously going to those aspects, but keep in mind that obviously, or the take home message is that the redox reactions are prevalent everywhere in all the systems that you more or less set sight upon, right. And certainly as an environmental engineer, redox reactions are probably the most relevant reactions that you would usually come across, right. So again, that is with respect to the applications, and then I believe we moved on to looking at how to balance different redox half reactions, right. So let us look at all that. Let us say for a second, let us summarize that, right. So here I guess what do? We need to identify, or we are going to talk about briefly, balancing redox or half reactions, redox half reactions, right. So the first aspect would be obviously, right, you need to identify the couples, identify the redox couples, and I believe in our example in the last session we looked at, I believe, oxidation state of not oxidation state, pardon me, oxidation of chromium 6, no, I believe reduction of chromium 6 to chromium 3 by sulfur dioxide, right. So I believe that was the example we looked at earlier, but here we are only going to summarize what we have been up to. So obviously we are going to identify the redox couples, then we need to calculate the oxidation numbers, right, to look at what now, change in oxidation states, right. Yes. So again, how do we calculate these particular oxidation numbers now? I believe we looked at a set of rules, but in general more or less the major aspect that we need to keep in mind that this is a theoretical value, right. So this is that hypothetical charge that would exist on a particular atom, right. If the electron that is being shared between two atoms is assigned solely to the more electronegative of the two atoms, right. So obviously let us say if there is a partial transfer, not a complete or full transfer of the relevant electron, let us say, right, and this electron is being shared by atom A and atom B, but let us say because atom B is more electronegative than atom A, it would have, let us say, a greater share, as in greater than 50%, let us say, of the electron that it is sharing with A, right. So what is it, or how do I calculate the oxidation state here? So with respect to this electron, let us say I am going to assign this electron completely to B, right. So oxidation state here would be, let us say, -1, and here it would be +1 for A, right. So that is how we go about that. So obviously in that context we looked at, I guess, a few of the known, or in general oxidation states of different atoms that we come across. So usually oxidation state of oxygen is equal to -2, right, other than obviously if it is in the form of O2, right. Why is that? Because both the atoms here in O2, oxygen and oxygen, have the same electronegativities, right. So obviously the electron pair is going to be shared equally between the two oxygen atoms. So thus obviously the oxidation state of O in O2 would obviously be 0 here, right. So in this case obviously again usually of hydrogen it is going to be equal to +1, right, and usually for chloride, let us say, or chlorine, pardon me, it is going to be equal to -1, or chloride, right, of chloride, pardon me. But keep in mind that in general oxygen is more negative, electronegative compared to chloride. So if there is ClO4 minus, let us say, perchlorate, so the electrons would be, let us say, what do we say, oxygen being more electronegative, you need to take into account that the oxidation state of this particular oxygen atoms, or these oxygen atoms in ClO4 minus, would be -2, and then calculate the oxidation state or number of the chloride atom accordingly. So let us just do that. Let us say oxidation state of Cl plus 4 times oxidation state of oxygen will be equal to -1, right, and Cl -8, 4 times -2 is 8, -8 -1. So oxidation state of chloride here is equal to +7, right. So that is what you see here. But in general with most other what do we say compounds, relative to most other compounds, Cl is electronegative, right. So again in general this is the particular way, right, we more or less sum the oxidation states and equal that to the charge on that particular anion or the cation, and obviously if it is neutrally charged molecule it is going to be 0 here, right, it is charge balance more or less. And but obviously keep in mind that here we are calculating the average oxidation state. But for example, in let us say your particular organic compounds, sometimes let us say the average oxidation state of a particular atom can be confusing. Let us just look at one example here. So, let us say acetic acid CH3 COOH, right, CH3 COOH, right. So, here let us say let us try to calculate the oxidation states of these two particular carbon atoms here, right. So, again keep in mind that how do we go about assigning the relevant oxidation states or numbers. So, if a relevant what do we say electron is shared between two atoms, we look at which of the two atoms is more electronegative and assign that particular electron to that particular atom, right, and then calculate that particular charge accordingly. So, obviously on carbon here, right, it has 3 bonds, right, it is with H, right, and one with carbon. Carbon and carbon, right, both have the same electronegativity, thus no particular what do we say assigning there, right. So, how do I calculate the oxidation state of carbon? It is going to obviously be -3 plus 0. So, that is going to be equal to -3. Why is that? Why do we have -3 here? Because we are assuming that the electron that it shares with hydrogen is what do we say going to be or what do we say carbon has a greater share of the electron that it shares with hydrogen. So, that is why we assign -3 here for the 3 hydrogen atoms we see here, and 0 because for the one electron that it shares with the other carbon here, let us say 1 and 2, let us say carbon 2, both have the same electronegativity. So, both share the electron equally. So, again -3 here. So, with respect to carbon 2, let us say this is with respect to carbon 1, and with respect to carbon 2, let us say what do we see here now? Again carbon carbon share, so that is 0 there. With respect to oxygen, oxygen is more electronegative, so I am going to say -2 there, right. And again OH, OH already has 1 here, so it will have -1 here, right. So, plus because oxygen is -2, oxygen is -1 here, the share here. So, that is going to be equal to +3, right. Again carbon and carbon, let us look at what we did. Carbon 2 and carbon 1, right, both have the same electronegativity. So, thus let us say no particular influence from that particular electron share there on the oxidation number. But with respect to oxygen share, let us say the 2 electron pairs, let us say there, right, or the 2 electrons being shared by carbon with oxygen, right. Oxygen being more electronegative than carbon, we are going to assign those electrons to oxygen. So, thus +2 charge, right, for this particular case, and obviously +1 from this particular case here, right. So, with that we end up with +3, but you see that the average oxidation state is going to be equal to 0, right, of carbon. The average oxidation state of carbon in your particular acetic acid is 0, and obviously how can we obviously calculate that? It is CH3 COOH, right, oxidation state 2 times oxidation state of carbon, right, plus 4 times oxidation state of hydrogen plus 2 times oxidation state of oxygen, or number, pardon me, right, is equal to 0. So, 2 NC plus 4 times 1 plus 2 times -2 is equal to 0. So, obviously again these two cancel out. So, you see that oxidation state or the average oxidation number of carbon in acetic acid is 0. But as you see the carbon the 2 carbon atoms here right in this acetic acid have different oxidation states or oxidation numbers, right. So, anyway that is one particular aspect that you need to be aware of, but in general I guess if you look at the average oxidation states I guess or oxidation numbers, pardon me, you should be able to glean the relevant information. Again, so let us move on, we digress. So, first we are trying to balance the redox half reactions. In that case we identify the redox couples, as in that particular case chromium 6 reduction to chromium 3 plus. So, Cr6 and Cr3, right, I think CrO4 2 minus and Cr3 plus, and SO2 and SO4 2 minus, those are the 2 redox couples. And then I calculate the oxidation states of chromium, right, in the redox couple, right, and also of sulfur, right, in the 2 on the redox couple there. And then what do? I guess I am going to continue here. So, and then I am going to assign the electrons based on the change in oxidation states or the numbers, right. So, I am going to assign the electrons accordingly. So, once I assign the electrons, then I need to move on to balancing the relevant elements, right. And how do I do that? In general, O I balance it with H2O and H with H plus, right? And obviously the other elements, chromium and sulfur, you need to look at that particular balance anyway, right? So we need to obviously balance the elements and then move on to oxygen and hydrogen, right? And I am going to balance oxygen by looking at substituting or having H2O, and hydrogen by having H plus, right? And then obviously I am going to do a charge balance, right? So more or less again we are going to have to calculate the change in the oxidation states to calculate the what do we say, number of electrons being transferred. You assign the electrons, then balance the elements and then check for the charge, and then you can get the overall reaction by summing it up accordingly, I guess, so that your number of electrons, right, that are being gained and are being accepted or lost, let us say, are accepted, right, are going to be the same, right, because you can't have an electron pool in solution. So again, now let us move on to the relevant aspects with respect to kinetics here. So obviously in redox reactions, right, disequilibrium is what is prevalent. So as we discussed earlier, right, many redox reactions are feasible, but because the kinetics are relatively slow for most of the relevant reactions, right. So kinetics play a very important role, right. So in general though, as what you would see out there is that even though many reactions are feasible, because they are way too slow, they do not go through. So in general the norm is that disequilibrium is what is the norm, I guess, right. Disequilibrium or redox disequilibrium is what you would observe out there, right. And why is that? Because the kinetics is too slow, or kinetics are too slow, right. So again one aspect is that we need to obviously consider the rates of the relevant reactions, right, whenever we look at the kinetics of a particular system. So here I guess we are going to look at a particular what do we say, example here, I guess, or not example, I guess a particular set of equations, and then look at a relevant model for a particular set of examples. So rate equations, just to refresh your memories, right. So let us say A plus B goes to C plus D, let's say, right, and what is the rate of this particular reaction or the forward reaction, let us say, if I can call that, it is going to be equal to rate constant of the relevant reaction, right, times the concentration of the reactants, right, raised to the stoichiometry. Here obviously I am the stoichiometric coefficients are 1, thus I am or let me write that down to be clearer, I guess, if it is A times A, not A times stoichiometric coefficients are A, B, C and D, right. So then the rate of the reaction is going to be equal to rate constant times A raised to its stoichiometric coefficient and B raised to its stoichiometric coefficient. So obviously again the take home message is that the rate of relevant reaction depends only on the reactants and not the products, right. So obviously again if you are looking at the backward reaction, right, you will have for the R backward, let us say, K backward, K forward, C to the power of C. But obviously when you are calculating R net, let us say, for each of these particular compounds A, B, C and D, then you need to take into account the relevant aspects, right. Again this is something we have discussed in great detail with respect to our kinetics section earlier when we discussed the fundamentals quite a few sessions ago, right. But we just keep in mind again that the rates depend upon the reactants and not the products, right. So again let us look at what we usually observe here. So let us say second order, right. So I guess that is the example that we just looked at, a second order reaction, and we know how to write the relevant rates of that particular what do we say, reaction. So obviously as you see initially let us say when you have high concentrations of these reactants, the rates are going to be high, and as the reaction goes through, the concentrations of let us say A and B decrease, right, because C and D are now formed, right. We are assuming that the case is that there is only the forward reaction is going through, right. Then obviously you see that the rate of the forward reaction is going to decrease, right, and obviously why is that? Because the concentrations of A and B are also decreasing, right. And obviously another case that we need to look at, or we have looked at too in the past, I guess, is a pseudo first order. I guess it is self explanatory, it is pseudo first order, let us say. Let us look at an example. Let us say, let us first consider an example of a second order reaction. Let us say A plus B goes to C plus D, right. So, we are going to start with an example of a second order reaction now, right. So, as we know what is the rate of this particular reaction, let us say rate of the forward reaction, let us say is going to be rate constant, let us say times concentration of A and concentration of B, right, the reactants here. So, here in this case of pseudo first order, let us say, and we are considering this particular example, what would the system be or behave like, let us say, if one of the concentrations of one of the reactants is far greater, let us say, than the concentration of the other reactant here, right. So, what is going to be the case here? Then let us say I can modify my what do we say reaction, let us say, or the rate of the reaction as K star times concentration of B. Okay. So, obviously, here what is K dash here, that is going to be equal to the original rate constant times concentration of A, right. And I guess if we look at this particular modified rate equation here, we see that it is a first order reaction, but we know that it is actually a second order reaction, right, or the origins are from a second order reaction, but it behaves like a pseudo first order reaction. Why is that? Because concentration of A is far greater than concentration of B. So, over the course of this particular reaction A plus B transforming to C plus D, right, the concentration of A being far greater than B, pardon me, the concentration of A being far greater than B leads to a system behaving like a pseudo first order, right, as in the change in A is so small compared to the change in B, so that you can consider the concentration of A to be a constant, and instead of having just rate constant here, we are going to have a modified rate constant, which is the sum of, not sum of, pardon me, the product of these two variables here. And here the applications are of this pseudo first order reactions are many, and mostly in natural systems and also in engineered systems, when you have, let us say, concentration of one of your what shall I say, the redox or reducing agent, let us say, to be very high, and let us say B is your target, let us say, you usually consider cases, let us say, when you add a lot of reducing agent to reduce your target, and applications in such scenarios and so on. Now, moving on to the next aspect, let us look at a couple of models. Obviously, you never need to mug stuff up, but you just need to understand how to be able to manipulate the relevant aspects if and when required, right. So, obviously, applications with respect to redox reactions or even the acid base reactions, right, are not limited to just the aqueous phase, even the gaseous phase or in the atmosphere, right. So, again different models out there. So, we are going to look at one particular model where we are going to have production of hydroxyl radical, right. Hydroxyl radical, again, as we know, has an unpaired electron. So, it has a strong tendency to accept an electron. So, it is an electron acceptor. So, it turns out to be a very strong oxidizing agent or strong oxidant, right. So, we can what do we say form hydroxyl radical in different ways, right. I am just going to look at two mechanisms here. So, obviously, hydroxyl radical, when it is formed, let us say, either in the atmosphere or you lead to its or you create the conditions to promote formation of hydroxyl radical in the aqueous phase, right. What do you see now? Let us say you are you see that hydroxyl radical would react with what it is you want or which is your target. So, hydroxyl radical will react with your target, but being a strong oxidizing agent, right, it does not have a preference, let us say, for only one particular compound or such, it is relatively non-selective, right. So, it will also react with the other particular compounds present in the solution, obviously depending upon the type of compounds, obviously, right, and the relevant rate constants or the rates, yes. So, obviously, what you see is multiple parallel reactions whenever you have these radicals what do we say in your solutions, right. So, what do we need to look at? We need to look at the relevant reactions with respect to what is the ratio of my particular radical reacting with the target compared to, let us say, its particular what do we say reaction with the scavenger. Scavenger is something, let us say, I would call an leading to, let us say, loss of a hydroxyl radical, let us say, right, or all these unwanted reactions, I would call them as scavenging reactions, right. So, anyway, let us look at one particular example here. So, I guess production mechanism, I think we can have hydrogen peroxide in the presence of ultraviolet light, right, can lead to formation of hydroxyl radical, right, and also ozone, let us say, depending on the pH that you maintain, usually at higher pH, can lead to formation of the hydroxyl radical, right, can lead to formation of hydroxyl radical. So, we just looked at two mechanisms just for your understanding. So, this can this is how people get it done in what do we say, within the presence of UV light, usually 254 nanometer wavelength, right, or UV photons, let us say. And obviously, if you have ozone present in your solution, or if you are bubbling ozone through your solution, and you have what do we say, or if you adjust the pH, in general you will have hydroxyl radicals being formed at relatively higher concentrations, I guess. So, let us move on. So, here we have two aspects, as in we just discussed that the hydroxyl radical can react with my target or targets, they can be multiple targets too, right, and form various products, right, various products. Or the hydroxyl radical being non-selective, it can also react with my scavengers, right, and form various products, right. So hydroxyl radical, here reacts with everything, right, not everything, let us say, right, but it is again the key is that it is relatively non-selective depending upon what is present in your particular water or the matrix, right. It is going to have the relevant parallel reactions. So, some of them would be with your target, which would be your reactions that you want to occur or promote. Some of them would be with your scavengers, right, which you would want to suppress, right. Again, and here rate with the target, right, rate of the reaction with respect to reaction with the target, and what is that going to be equal to? Rate constant, right, times OH radical concentration times the target concentration. So, keep in mind that when we write the rates here, though, finding out the rate would be relatively difficult in this particular equation as we have written down. Why is that? The hydroxyl radicals have remarkably low half lives. So, you cannot measure, or not cannot, let us say, it is remarkably difficult, right, to be able to measure the hydroxyl radical concentrations, right. So, that is one particular aspect that we need to keep in mind. And again, rate with the scavenger. So, rate the scavenger will be rate constant for this particular reaction, right, OH radical concentration into concentration of the scavenger, right. So, obviously, I am just using the generic term scavenger to what do we say, approximate multiple particular compounds that can lead to scavenging of my hydroxyl radical, right. So, here I have that. So, I want to be able to what do we say, play around with my particular equations, so that I get the relevant information that I am looking for, which let us say is how to be able to approximate or model the rate of the target in terms of rate of the production, as in let us say I can from these particular reactions calculate the rate of production of my hydroxyl radical, but I want to be able to get an understanding about how the target, let us say, or the rate at which the target is going to be removed by the hydroxyl radical, right. So, let us look at that for a second here. So, here keep in mind that we mentioned that OH radical has very low half lives, right, yes. So, in general, and also let us say keep in mind that the concentrations of these what we say hydroxyl radicals in solution are going to be relatively low. At no point in time would you have remarkably high concentrations, and obviously the reason, one of the reasons is that the half lives of these particular radicals are very low. So, we can assume that with time, right, the concentration of hydroxyl radical does not change, right, compared to obviously the rates of production and rates of production of the radical and rates of scavenging of the radical and rates of the reaction with the target. So, what we are assuming here is that because the OH radical concentrations are very low, right, and we can compare to the rates of the production or rates of reaction with respect to the scavenger or target, I can assume that, or I guess it is a good enough assumption that the hydroxyl radical concentration does not change with time, right. So, that is going to be equal to obviously what now, rate of production of the radical minus how is the radical being lost, either due to the scavenging reaction or due to the target reaction, right. So, this is what we have, and this is the assumption that we are making though. So, keep in mind that let us say OH radical concentration initially, right, and OH radical concentration let us say at time t can be pretty less, let us say 5% or so though, right. But with respect to time, let us say, and with respect to the relevant rates, this particular variable is very low or negligible, that is why we can assume it to be 0 here. So, here we have rate of, from this particular assumption, rate of production of the radical equal to rate of scavenging of the radical plus rate of rate of the reaction of the OH radical with respect to the target, right. So, and that is particular case, and then here obviously let us try to transform this particular equation. Rate of production equal to rate of scavenger is Ks OH radical times the scavenger plus K target, right, OH radical plus times the target, right. Again, what are we expressing here? The rate of production of the hydroxyl radical would be equal to the rate of loss of the hydroxyl radical, and which reactions are obviously leading to the loss of your particular hydroxyl radical. Hydroxyl radical either reacting with the scavenger or hydroxyl radical reacting with your targets. So, the relevant losses of these hydroxyl radicals, right, I can get them from the relevant rates of the relevant reactions, because the stoichiometry here we are assuming is 1, right. That is what I have here as in 1 times Rs and 1 times Rt, right. Again, so I have this particular case. So, OH radical let us say is going to be equal to rate of production, which I can measure depending upon the number of photons I am putting in or the amount of ozone I am putting into the solution. I can measure rate of production by Ks times scavenger plus Kt times this target concentration. So, again target concentration and scavenger concentrations are something or the are what I am presuming here that I can measure, and that is in general obviously what you would see, right. And you can measure the concentrations of the scavengers and the targets with time. But obviously here I still want to be able to come up with a way to approximate rate of the reaction of hydroxyl radical with the target, right. So, here let us say if I multiply that by OH radical times Kt times concentration of target, right, Kt times target, that is equal to rate of production times rate constant and target, right. So, I multiplied with this particular variable on both the sides. So, obviously what do I see here? You see this is nothing but rate of the reaction of hydroxyl radical with the target, that is going to be equal to Rp by this set of variables, right. So, here obviously if I look at this particular variable, I can measure target concentration, I can measure scavenger concentration, right. So, I can get the relevant information in this particular variable, and I know the number of or amount of photons or ozone concentration that I am putting into the system. So, I can calculate rates of production, right. So, once I have this particular information, obviously I can express rate of this particular loss of the target or reaction of hydroxyl radical with the target in terms of rates of production of the hydroxyl radical. So, again what will this help me with? So, once I know the rate of production of hydroxyl radical, I can also estimate the rate at which the target is going to be destroyed or not destroyed, let us say degraded, right, or how it is going to be at the rate at which it is going to be oxidized. Again, why are we having to get this model out? Because hydroxyl radical concentration relatively difficult to measure out there, but the way we have set it up now, we can now express the rate of loss of your particular hydroxyl radical or oxidation of your particular target in terms of variables that we can measure or such. And obviously, if you look at this particular set of variable here, right, Kt times T by Kss times Kt in T, what is that giving you an idea about? If you look at it, it gives you an idea about rate of let us say target with respect to rate of the production of your particular radical, right. That is what we see here, right. This particular variable, let us say I call that x, right. X is nothing but the rate of loss of your hydroxyl radical while degrading the target, right, or rate of degradation of your target if you can transform with respect to the coefficients by rate of production of your particular what do we say hydroxyl radical, right. So, this will give you an idea about how efficient is your process. Obviously, the higher the value of x or this variable, the more efficient the process. But let us say if your scavenger concentration is very high, right, what happens in that case? If the scavenger concentration is very high, right, what would you see? Obviously, the value of x would decrease, right. So, that is what you would see here. But if the value of this target is high or the concentration of the target or Kt times T is high, what would you see then, right? You would see that rate of target would be equal to rate of production, right. Let us just write that down here. So, I have rate of reaction or rate of loss of hydroxyl radical during its oxidation of the target would be equal to rate of production of the hydroxyl radicals times Kt concentration of target by Ks S plus Kt T, right. So, let us just try to understand this system, I guess, right. So, in which cases would your system be inefficient? Either when your scavenger concentration is very high or your rate constant is high, right, or when this variable is high, and this variable obviously can be high when either the rate constant is high or the scavenger concentration is high. Again, as in what does that mean? Relatively high compared to Kt times T. What does that mean? So, if your hydroxyl radical preferentially reacts with what do we say, the scavengers in relatively or the reaction of the hydroxyl radical with the scavenger is relatively faster compared to the reaction of this particular hydroxyl radical with the target, obviously your system is going to be inefficient, or even if the scavenger concentration is going to be relatively high, right, that is what you see here, your system is going to be relatively inefficient, right. But obviously if you see that the inverse of it, as in when will this variable be high? When either Kt is high or the target concentration is high, right. Yes, that is what you see here. But and when would that occur? Obviously either the target concentration is high relative to the concentrations of scavenger, or let us say when the hydroxyl radicals reaction rate is faster with respect to, or the kinetics of hydroxyl radical reacting with the target is faster compared to the kinetics of hydroxyl radical reacting with the scavengers, right. So, in that case let us say if this variable is high, right, what would it turn out to be? RT would more or less be equal to Rp, right. In that case obviously the system would be efficient. But obviously as you would see though, as the hydroxyl radical keeps reacting with the target, what happens to the concentration of the target? It keeps decreasing, right. So, obviously the rate at which this target is going to be oxidized is going to keep decreasing with time, and that is what you would observe later on too, right. Again that is for our particular understanding here, right. So, let us move on to one particular aspect or another aspect, I guess. So, competition kinetics. So, obviously here as we just looked at our particular earlier model, we have multiple targets, we have multiple scavengers, right, as in we have OH radical, it can react with either the target or the scavenger, right. So, it is competition kinetics more or less, right, different parallel reactions occurring there, right. So, obviously here let us say usually let us say I know the rate constants with for this particular reaction, let us say, of how the hydroxyl radical would what do we say, the kinetics of the hydroxyl radical reacting with the scavengers. But for my particular target I do not know the rate constant, let us say, right. So, how do I calculate that? So, let us just look at that briefly. So, I have hydroxyl radical plus target going to products, right, and hydroxyl radical plus scavenger going to products, right. And if I can write dt with respect to d time, right, and how is the concentration of what do we say target changing with time, right. So, here we see that it is not being produced, it is only being lost. So, it is going to be equal to minus rate of this particular target reaction, right, and that is nothing but equal to minus, right, rate constant K target, right, or let us say this is K target, right, times OH radical times the target concentration, right. And then obviously again what do I have here? That is going to be, let us say if I look at it, that what can that what is this form like? So, we have dt or differential of the concentration of the target with respect to time equal to the rate of loss of that particular target, and we know that the relevant what do we say rate for that particular reaction is here. So, let us just try to see what we can express that as dt by concentration of T equal to minus Kt OH radical times dt, right. So, obviously getting information about OH radical is relatively difficult, but let us say if I integrate on both sides here. So, natural logarithm of T, right, by T naught is equal to minus Kt integral of OH radical times dt, right. Again I do not have this particular value because I can't, or difficult to measure, let us say hydroxyl radical concentration. But let us say if I do the same with respect to this particular reaction or with respect to the scavenger, right, and what am I going to end up with? Natural logarithm of the scavenger by S naught equal to minus rate constant of the scavenger times OH not times, pardon me, times the integral of OH radical times dt, right. And now I can cancel these out, and I can measure T and T naught and S naught, right, and I can measure target and scavenger concentration with time. So, I have Kt and Ks. So, I can have what do we say, how do I go about this system now? I already have Ks, right. I want to calculate what is Kt, right, but I have T naught and S naught, right, and I know how T and S will change with time, right. With different times I know how the target concentrations and scavenger concentrations are going to change. So, with that and this particular equation that I have here, right, I can conduct regression and then get the value of that particular Kt, which would obviously give me the least sum of squared errors or minimum sum of squared errors, and then that would obviously be my Kt. So, obviously when you have computation kinetics and you know the rate constant of a particular set of what do we say reactions, you can use that to calculate, I guess, you can use that to build upon the model to calculate your unknown rate constant, right. So, I guess with that we will end today's session, and we will carry through continue looking at kinetics for a few minutes in the next session, and then move on to equilibrium, I guess. And I guess again with that I end today's session. Thank you.